All right, looking at number 6 here, it tells us that liquid ammonia boils at negative 33.4 degrees Celsius, has a heat of evaporation of 23.5, and it wants us to calculate the vapor pressure at negative 50. Ooh, that might have got missed, but that's dropped off the side. All right, whenever we have our vapor pressures and heat of vaporization, we're using this odd little equation that actually has a natural log of pressures, and it's technically the vapor pressures, and we're going to take the negative of the heat of vaporization divided by an R, and then 1 over T2 minus 1 over T1. The only unit we have to worry about too much, we want the heat of vaporization to be in joules, and that's because we're going to use an R that's in joules, and we'll want our temperatures in kelvins. All right, so I only know that it boils at 33.4, so I'm going to say this is my T1, but my P1's not really given. But since this is talking about boiling point and it kind of implies at normal pressures, we're going to say P1 is normal atmospheric pressure. So I'm going to do this as 1 atmosphere. 1 atmosphere. We're going to solve for P2. Now, heat of vaporization, I said we want this in joules, so I'm going to write in 223,500 joules per mole. Now, we introduced R last chapter as a Gauss constant, and it still is. But in that previous chapter, our R had a value of 0.08206 liters, atmospheres, moles, and kelvins. Well, now we want an energy unit, and it's actually the exact same value. It's just if we go through the unit conversion to turn the liter atmospheres into joules, we would get 8.314 is the same as the 0.8206. So we're using this 8.314 because it has joules in it. And the only math I really will need to do is the two different temperatures. So I have negative 50, so 273 minus 50. T2 is 223, and T1 is 273 minus 33.4. $239.6. Now that one I have, and I'll have to do 2 here, units. All right, now we're kind of ready to solve for this pressure, which is a little bit trickier than math we've had to do so far this term. So we're going to solve everything on the right, and I'm going to start with my parentheses first. So, and rather than type 1 over 223, I'm actually going to get my calculator to do that by doing 223.2 and use that x to negative 1, and then subtract 239.6 x to negative 1. Then I'll multiply that by 23,500. That's not zeros. And divide by 8.314. And I'll need to put this negative in. All right, now that's everything on the right. Now I need to get rid of this natural log, and the way we're going to get rid of it is take the inverse of it. So on my calculator, you see a natural log there. The inverse is that e to the x. So I'm making the inverse natural log of the value we just got. Now technically this value should be equal to our P divided by, or P2 divided by P1. And since we used a P1 of 1, that value there is our second pressure. So P2 is 0.420 atmospheres. Now what we're seeing is we lowered the pressure, or we lowered the temperature, and since we lowered the temperature, the vapor pressure went down. And that is typically what we see for all substances. About the only way it would actually go up is if the heat of vaporization was somehow a negative value, and it will never be. So you can guarantee if you lower the temperature, you're lowering the vapor pressure.